Modern motor vehicles are packed with high-tech electrical systems and electronic controls. If you don't understand the very basics of electrical, performing diagnostics on such vehicles will only ever be a hit or miss exercise. Hi, I'm Haddo. In this video, we're going to cover some of the most fundamental electrical principles using the analogy of water to help us. Let's start by looking at this tap. What's inside the pipe? Water. If I cut the pipe with a hacksaw, what happens? Yes, water would spurt out. That's because the water is under pressure. For training purposes, I've made up this water pipe demonstration kit and I have a pressure gauge teed into the pipe. For this demonstration, I've wound up the pressure as you can see here on the pressure gauge. I'll snap open the tap and as you can see, I have a lot of water flow. We'll try that again, but this time I have very little supply pressure as you can see on this gauge. Now let's see what happens when I open the tap. As you can see, I have very little flow. So pressure is the force that is required to make water flow. It's similar to voltage in an electrical circuit. Voltage doesn't flow, but it's the force needed to create flow. No pressure, no flow. In other words, voltage is electrical pressure. As you can see, I have a hose coming off the tap. The hose is like a conductor because it stops the water leaking out. The hose has a ball valve fitted to the end to simulate a hose trigger nozzle. I also have another ball valve to simulate a kink in the hose, but it's not completely blocked off. For training purposes, I've added some more pressure gauges as well. You can see we have quite a bit of pressure on this gauge. The other gauges are zero as the tap is turned off. If I turn the tap on and have the last valve off, what happens in the hose? As you can see, the pressure is the same throughout the hose, even after the restriction. I'll vary the kink and you will see that it makes no difference when I have no flow. We're seeing this because of Pascal's principle, which states pressure is exerted equally in all directions without loss, but only in a confined space. Now, let's turn on the last valve and get some water to flow. Look what happened to the pressure. It dropped after the restriction. But stop the flow and the pressure builds up evenly again. Current flow is very much like water flow. Current is measured in amps and is the flow of electrons through a conductor. So we now know voltage is electrical pressure and current is the flow of electrons, but what is resistance? So if you research the definition of resistance, it will say resistance opposes the flow of current. But I like to think of resistance as resistance controls the flow of current. Here I have a lot of water flow, but I can easily control the flow by adjusting the size of the kink or resistance. The more I kink the hose, the less flow. Okay, let's put all this into an electrical context. This battery is like the water pressure in the pipe. It's basically a pressure storage device. The switch is like the tap, but it'll either be on or off. The electrical wire is like the hose and the globe is like a fixed size kink. I have another switch which is just like the on-off valve at the end of the hose. I'll use some voltmeters to measure the electrical pressure, which is voltage, and an ammeter to measure electrical flow, which is current. With the switch turned off, I only have pressure in the battery, just like the water pipe. I'll turn the first switch on, but have the last switch off. Remember, that's the same as having the tap turned on and the last valve off. There we go. Just like in the water demonstration, the pressure builds up in the circuit. But look what happens when I start the current flow by activating the last switch. Just like when we activated the last valve and the pressure dropped after the resistance, the same has happened in this electrical circuit. Let's see what happens when we have no resistance in an electrical circuit. Here I have a battery and two wires. Let's see what happens when I join them together. That didn't end well, did it? Why? Because I had nothing to control the current. Let's try that again, but this time I'll have a test light in the circuit. See, no problems, as I had a resistance or a load to control the amount of current. So what have we learnt? Voltage is electrical pressure, current is the flow of electrons, and resistance controls the flow of current. If I increase resistance, current flow will drop, and vice versa. We also found that resistance only becomes effective when current is flowing. No flow of current, the pressure builds up evenly throughout the circuit. Here's a few more important things to remember. The symbol for voltage is E, which stands for electromotive force, or the letter V. I like to use V for volts. The flow of current is measured in amps or amperes. The symbol is I, which comes from a French term roughly translated as intensity of current, but most people use A for amps. Finally, resistance is measured in ohms with this symbol, which is a Greek letter for omega, but we just use R for resistance. When we buy electrical tools or light globes, we often refer to the wattage. Wattage is the measurement of electrical power. Think of wattage like the combination of water pressure and flow to turn a water wheel. You need both to turn the wheel. If I increase the pressure or increase the flow, the wheel will turn with more power. Wattage equals amps times volts. With a stable voltage supply like in our vehicles, to increase the electrical power, we have to increase the current flow. When diagnosing faults on late model vehicles, this fundamental knowledge will be your best friend. Make sure you watch our other videos in this course to keep building your electrical knowledge. I'm Haddo, keep training, and thanks for watching.